Hello everyone, welcome back to another lesson in integral calculus, and in this video we will talk about solid revolution. So in this video we will learn to compute volume of a solid being revolved, okay, or an area being revolved about an axis. What is the concept? Why is it known as a revolution? Now, for example, if this is the area and this area here, it's the area bounded by this curve. Let's say this curve is a function of x, and we have a line here. Let's say this is x is equal to a, and this one is x is equal to b. Now, if this area is being revolved about the x-axis, we would come up with this solid figure, correct? So if we revolve this area, then we will have this solid figure. Now, our goal here is to compute for the volume of the solid. However, take note, our volume here has an irregular shape due to irregular curve that we had. By looking at this one, we cannot compute the existing volume formula that we had in our geometry, such as the volume of a rectangular prism, pyramid, cone, and so on. And that's why we have to apply integration. Again, integration is very helpful, especially when computing for the areas and volume of a irregular shape or irregular figure. Okay? Now, how are we going to apply integration to this one? Now, take note, if we try to cut the solid here at any point from this limit here, let's say this is A, and this one is B. So if we try to cut at any point, we would see a circular cross-section, correct? That is a circle at any point from A to B, okay, from A to B. Now, the concept of integration here is that the same as with the area, in computing for the area, we divide this region into infinitely small rectangular strip, correct, in which this one is our derivative of x that is very small or thin, that is changing with respect to our x coordinate. Now, the same as with this one, we can divide our figure into a very or infinitely small disk, okay? Now, we have different method in computing the volume, and the easiest method is we have the circular disk method, in which in circular disk method we divide the solid figure here into a very small, or let's say infinitely small disk, okay? So what is a disk? A disk is a solid shape like this one. Now, the same as with a coin, that's an example of a disk. We also have a frisbee disk, okay? So those are example of a disk figure. Now, in this figure, we divide this into a very small disk that runs through its limit from A to B, and then we compute the volume of that disk, of every disk from A to B. Then we add that volume to come up with the volume of the entire figure. So the same as with the concept of area. So we divide, again in the area, we divide the region into a very small rectangular strip. We sum up all the areas of the strip to come up with the areas of the entire region. Okay? But how are we going to compute for the volume of our disk? Now, take note, our disk is just a cylinder being compressed, okay? So it is just a cylindrical having a very small thickness or very small height, just like this one, in which this is the height. This one is the height, correct? And we know that the volume of a cylinder is pi r squared h from our geometry. So we have the volume is equal to pi r squared h, where our h here, this is the height, and r here, that is the radius from the center of our disk, okay, to the outside surface. Now, since in the figure we have a very infinitely thin disk, so therefore we could say that our height here, like in this one, that gives us the derivative of the height, correct? Since again, this is the same as with our area, in which this could be derivative of the height, or the change in the height that runs through A to B. Okay, so the same as this one, then we could have our volume is equal to pi r squared, then our height here, that is the derivative of the height, that is the d8. Now, we know that if we apply integration, we need to have a function of any variable, function of x or function of y. But looking at the 2D plane, again, this one is the radius of our disk. Okay, so this one is the radius of our disk, and this is the height. Now, our radius is from the axis of rotation to the top surface or the bottom surface. Okay, now we know that our r here, that's just basically the y of our function, the y coordinate at any point, in which we know that our y here is just a function of x, correct? So therefore, we can say that our volume is equal to pi, then our r here, that is the y or the function of x, then it gives us function of x squared, and our h here, that is the derivative of the height, this one, so this gives us the derivative of the x, correct, since it is an x-axis. So this one is the derivative of the x, so therefore we have dx. Then we can now integrate from the limit a to b. So this is the general form for our disk method. Again, this is just a volume of a cylinder, in which we have our height here, that is referring, or that is changing from the limit a to b, and our y here, that is just the function of x of the curve. Okay, that's how you need, that's the concept of a circular disk method. Now let's try to apply this concept in solving a problem. Now, I have here the area bounded by curve x squared is equal to 2y, and y is equal to 8, and x equal to 0. Find the volume generated when it is revolved about the y-axis. So if we have the area bounded by this curve and these lines, and that region is being revolved about the y-axis, so we need to compute the volume generated. But the first thing we do here, of course, to plot our curves in our Cartesian plane. Okay, now this is a parabola, since we have x squared is equal to 2y. Now, this parabola here resembles, or is in the same form with our general equation of a parabola, which is x minus h squared is equal to 4a y minus k, correct? In which we have our h and k here is equal to 0, and we know that h and k is the vertex of our parabola. So therefore, we can say that our parabola here, or the vertex of our parabola, is on the origin of our Cartesian plane. So let's try to draw. Now we have this parabola. Again, our vertex, or the minimum point of our parabola, is located at the origin, or at 0, 0. Now we have our line, that is y is equal to 8. So therefore, if we plot y is equal to 8, it is just a horizontal line, correct? So y is equal to 8 is at this point. So we have here, this one is y is equal to 8. Okay? Now again, this curve is equal to x squared is equal to 2y. And then we also have x is equal to 0. X equal to 0 is just the y-axis. And this is x is equal to 0. And then we compute for the point of intersection, so that we could determine our limit, or the limit of our area. So the point of intersections are this one and this one. And we know that this point of intersection here is just, we use this curve. Again, our y is equal to 8. So we know that our y here is 8. So we can now compute for the x by just letting our y here as 8. So x squared is equal to 2 times 8. Then we have x is equal to 16. That's square root. Then if we square a value, then we would have two possible roots, that is plus minus. So we have x equal to plus 4 and negative 4. Okay? So therefore, we have the point of intersection, which is positive 4 and 8 at this point, while at this point we have the point of intersection, which is negative 4 and 8. Okay, since we have the area here which is bounded by the curve x squared is equal to 2y, the line y is equal to 8, and the line x equal to 0, then we have the area or the region, which is this one. Now from the problem, this area is revolved about the y-axis. Okay, so if we revolve this region with respect to the y-axis, then we would come up with this solid figure. And then from the geometry, this solid figure here is what we call paraboloid, a paraboloid. Obviously, it is known as paraboloid since we have a parabolic outside surface, correct? What do you have in mind that we could compare to a paraboloid? I guess I have a bell in mind. So if you have seen a bell, so it is the same as or shape with a paraboloid. Okay? So if you have other things in mind, so you can comment it down. Our goal here is, of course, to compute the volume of this paraboloid. So again, we have a circular disc method in which we have to draw a disc inside this paraboloid like this one, and we can apply volume formula here by first expressing our integration as the volume of the disc, and we know that the volume of our disc is equal to pi r squared h, where in our r here, that is from the axis of rotation to the outside tip of our disc, and our height here is the thickness, this one. Since we know that our disc here has a infinitely small thickness, then we could express that as derivative of the height. Okay? Now we can change r and h here in terms of x and y respectively. Then we know that r here, this is x. Okay? And our derivative of height here could be expressed as dy, or the derivative of y. Then we have our volume is equal to pi, our r is x squared, our h is dy. Okay? Then we can now integrate. Now for our limit here, we know that our disc runs through from the origin to y is equal to 8. So at this point to y8. So we have our limit, which is from 0 to 8. Since we need to integrate this function in terms of y, then we need to change x squared here into function of y. And then from the curve, we have x squared is equal to 2y. Then we can directly substitute x squared here as 2y. Or we can directly change here x squared as 2y. So we can say that it is volume is equal to pi, our x squared is 2y dy, and our limit is from 0 to 8. So we have our volume, then we can take 2 pi outside of the integration, then we have 2 pi, the integration of 0 to 8, and we have y dy, then we can integrate y here, this is power rule, and we have y squared over 2 and the limit from 0 to 8. So we can substitute the upper limit inside, then minus the lower limit inside the function, then we have our answer here as 201.062. And since we know that this is volume, then we have a cubic units. So this is the volume of the solid generated by revolving this area about the y-axis. So this is our answer. And then we have example here. The area bounded by the curve y squared is equal to 4x minus 8, x is equal to 5, and x-axis is revolved about the x-axis. So we need to compute the volume. Now, the first thing we need to do here is, of course, plot our curve and lines in our Cartesian plane. Okay? But we need to identify first the vertex of our parabolic curve, in which we have y squared is equal to 4x minus 8. And we know that this equation is the same as with the general equation of a parabolic curve, which is y minus k squared is equal to plus minus 4a x minus h. So we can locate the vertex by changing this form into the general form of the parabola, and then we could say that it is y minus 0 squared is equal to, now take note, in the general form we do not have coefficient of x, or we have one coefficient, then we can take out 4 outside, or we can factor out 4 here, then we have 4 times x minus 2. Since if you distribute 4 inside the parenthesis, then we have this 4x minus 8 as the result. Okay? Now this positive, so therefore we have our parabolic curve opening to the right. So therefore we can say that our h here, or that is the x coordinate of our vertex, from this general form, our h is equal to 2. And our k here, from the general form, our k is 0. Thus, we have 2, 0, which is the vertex of our parabola. Okay, since we have already determined the vertex, and we can now draw our curve in our Cartesian plane. This is our curve, okay? Then, we have its vertex at 2, 0. Okay, this point here. Now, we still have a line, and our line is x is equal to 5. Then, plotting x equal to 5 gives us a vertical line. This one, this is x is equal to 5. And then, we have the x-axis. Then, this one, okay? That is x-axis. Or, we could say that it is when y is equal to 0. Okay? So, where is the area that is bounded by the curve and the lines? So, we could say that the area is this one. Okay? Now, our area is revolved about the x-axis. So, therefore, we will have this solid figure. Again, this is still a paraboloid since we are rotating a parabolic area about an axis. So, we can use, again, circular disc method by putting a circular disc inside our paraboloid. Then we have here our circular disc. This is our circular disc, in which this is the radius and this is our height, or the thickness, or let's say that is the derivative of height. Again, since we have the thickness of our circular disc infinitely small. So we can now compute the volume by first computing for the volume of that disc. Then we have the volume is equal to pi r squared h. That is the volume of a cylinder. Then the volume here is equal to pi. Now take note, our r here, this is y, correct? Since this is vertical, our radius is vertical. So we have here y. Then it is being squared. Our height here, since it's horizontal, then it is equal to the derivative of x. So we have dx. Then we can integrate this one. Now our limit, since our disk runs through from this point, let's say that is at x equals to 2 up to this point here, in which we have x is equal to 5. Correct? So therefore our limit is from 2 to 5. Okay? Now, since we are integrating it with respect to x, therefore, we need to change our variable y here into a function of x. Now, we know that our curve here has an equation of y squared is equal to 4x minus 8. Then we can say that y squared here is equal to 4x minus 8. So we can change that into 4x minus 8. So we have 4x minus 8, then dx. Then we integrate, we have, you can distribute pi inside the parenthesis, then integrate our function separately, then we have 2 to 5, or the integration of 4 pi x dx from the limit 2 to 5 minus the integration of 8 pi dx from 2 to 5. Then we have here 4 pi x squared over 2 minus 8 pi x limit from 2 to 5. Then we substitute the upper limit and the lower limit. Then we have the value of our volume, which is 18 pi, or that is 56.549. Then since this is volume, then we could say that is in cubic units. And this is the volume generated by revolving our area about the x-axis. And this is our final answer for our question number 2.